Iron, aluminium and silicon. An alloy module that is made of 3 common elements. When you put your hand over it, the electricity is generated by the body heat. Thermoelectric materials contributes greatly to the environment by reusing waste heat. But up until now, they were made by elements rare and harmful to the environment. NIMS developed new thermoelectric materials using elements that are very common. Producing liquid hydrogen is indispensable for the hydrogen-based society. With the development of high-performance magnetic materials and superconducting magnets. NIMS established the world's highest-performing magnetic refrigeration system. NIMS is Japan's sole public research institute specializing in material science. Cylon phosphorus, when excited with blue LEDs, becomes a superior light source and have changed the world of lighting. Ultra-heat resistant superalloys saving annual fuel costs by $1 million per plane. NIMS is continuously producing environmentally friendly materials to change the world's aeroplanes, contributing to the reduction of CO2 emissions. And lastly, the development of high-performance magnetic materials that are essential for next-generation vehicle technology. All things necessary to our lives are made from materials. NIMS has created a number of materials that have made a global impact since 2001 in a variety of fields, from metals to nanomaterials. In recent years, NIMS have been putting energy into the fields of environmental materials research, including the thermoelectric materials shown before. Thermoelectric materials make waste heat a treasure. However, they are not widely used today due to their high cost and toxicity. Thus, we have to consider environmental issues before being marketed. For these reasons, NIMS has developed new thermoelectric materials. Its cost is less than 1/5 as much as before. With its high level of safety and low load on the environment, it is attracting great attention from the world as an innovative material. This is because it contains only iron, aluminium and silicon. This result triggers the widespread use of thermoelectric power generation through waste heat utilization. Dr. Yoshiki Takagiwa, the researcher in charge, focused on iron and aluminium, typical abundant elements. As a survey, he conducted first principle calculations on the materials containing iron and aluminium to evaluate the feasibility. As a result, he found the addition of silicon to the iron aluminide system enhances the thermoelectric property. Furthermore, he used material informatics to determine the composition of the 3 elements. After determining the composition of both the P-type and N-type materials, he began making an actual prototype. He prepared a powder mixture of iron, aluminium and silicon as determined in the previous step. Then he melted it with an arc melting furnace to make an ingot. Finally, 2 types of alloy pieces were arranged in a package to obtain a new thermoelectric device. Let's check if it actually generates electricity. Gently place a finger. Here comes the electricity. As a result, electricity can be generated if there is a temperature difference of 5 degrees Celsius. Now we have thermoelectric materials containing only iron, aluminium and silicon. It is highly suitable for a power source for micro devices. We're now heading for a super smart society, uniting real and cyberspaces, namely Society 5.0. Microsensors play a key role to realize this smart society to come. However, there still remains a big issue of their power supply. In this case, Dr. Takagiwa succeeded to generate electricity from a slight temperature difference, large enough to drive the sensors and to transmit its data to the computer wirelessly. All the electricity needed is produced by the difference of temperature in the space. In terms of cost, it's about 1/10 of the conventional materials. In terms of materials, it is highly environmentally friendly. We cannot expect any more. When we think about its use as a power source for sensors in the IoT, which will become widespread in the future, we think it will not be a replacement for conventional materials, but rather a driving force for creating new value and products. NIMS is currently focusing on a project to liquefy hydrogen for the realization of a hydrogen society. We are focusing on the development of highly efficient cryogenic refrigeration technology to produce liquid hydrogen with low energy. NIMS already has a world record efficiency of liquefaction. We have succeeded in improving liquefaction from a limit of around 25% to 40% at the lab level. Magnetic refrigeration is an efficient cooling technology in which temperature drops when a strong magnet is removed away from a ferromagnetic material. To achieve even greater efficiency, the development of high-performance magnetic materials and superconducting magnets are key, and NIMS is now working on the development of both materials at the same time. For magnetic materials, we use data science to synthesize materials that are predicted to have high performance and aim for practical use. On the other hand, NIMS has been traditionally strong in the field of superconducting magnets for hydrogen liquefaction. Currently, we are trying to develop a new superconducting magnet for liquid hydrogen production that can be used at higher temperatures. By combining ferromagnetic materials and superconducting magnets, we are also developing a high-efficiency liquefaction system. Additionally, it is necessary to deal with the degradation of mechanical properties of metals used in cryogenic environments to store and transport liquid hydrogen. NIMS has been conducting endurance tests on the materials for liquid hydrogen rockets for more than 20 years. By making the best use of these achievements, we are conducting research for a safe hydrogen society. By developing new materials, NIMS is a research institute that aims to save energy, preserve the environment, and build a sustainable society.
The history of NIMS goes back to 1956, when the National Research Institute for Metals was established by the Japanese government. 10 years later, another institute for research in inorganic materials, such as ceramics, was established. In 2001, they were merged to create NIMS, the National Institute for Material Science, as a world's core material research institute. At that time, new fields such as polymer and biomaterials were added to cover the full range of modern materials. The total number of NIMS personnel is around 1,600, and half of them are researchers supported by technical and administrative staff, as shown in the table. The numbers in the brackets show permanent staff. NIMS is located in Tsukuba Science City, only about 70 km northeast from central Tokyo. NIMS Research Division consists of 7 research centers focusing on these materials. NIMS researchers are classified into various research fields as shown in the pie chart. Among them, the Center for Energy and Environmental Materials is most deeply engaged in research topics connected to the subject of RD20. We will present major research activity of NIMS related to renewable energy and reduction of environmental load in the following slides. NIMS established a research center for materials technology related to liquid hydrogen in 2019, which is key for the realization of hydrogen society. The right-hand figure shows a hydrogen liquefier system using magnetic refrigeration materials. This system is expected to be much more efficient than the conventional mechanical system. NIMS is now exploring new magnetic refrigeration material with excellent characteristics and developing a prototype of such a refrigeration system shown in the figure. Recently, by using machine learning, we have succeeded in discovering the world's highest performing magnetic refrigeration material, holmium diboride, which can operate near the hydrogen liquefaction temperature. In addition, NIMS has a plan to build test facilities for materials evolution in the cryogenic hydrogen environment. It is expected that integration of generation, transportation, storage and utilization technologies of liquefied hydrogen will make a reliable hydrogen supply chain for society. To realize this, however, basic data on the mechanical properties, durability and hydrogen compatibility of structural materials is essential for the design and manufacturing of products and facilities used in the liquefied hydrogen. NIMS started research on mechanical property evolution of materials at cryogenic temperature in the 1970s. Up to now, we have contributed to standardization of testing method at cryogenic temperature through Versailles project on advanced materials and standards and the failure analysis of the Japanese launch vehicle H2 number 8. Since then, NIMS has been evaluating mechanical properties of material used for liquid fuel rocket engines and contributed to increase their reliability. We believe that the technologies and experiences accumulated through these activities are also useful in evaluating materials for liquefied hydrogen infrastructure. Batteries are an indispensable technology for efficient use of renewable energy, and NIMS has been very successful in battery research. Optimization of electrolyte composition in the lithium-ion battery is a very important issue, and a large number of compositions needed to be tested. NIMS researchers developed a high-throughput combinatorial testing system using AI. By using this system, we can conduct screening for electrolyte across 1,000 compositions within a day. As a result, a specific combination of 5 compounds was identified to improve the performance of lithium-air batteries. For all solid-state battery research, we found that the high resistivity of the lithium cobalt oxide anode comes from reduction of lithium-ion concentration at the anode electrolyte interface. A new buffer layer to counter the problem was developed and the battery performance was remarkably improved. To support and promote battery research in NIMS, there is a specially designed laboratory with the most advanced characterization and analytical equipment installed over an area of 340 square meters. In the super dry room, we can assemble and evaluate newly designed battery cells without exposing to moisture. NIMS is also working on materials for sustainable energy generation. Examples shown here are next generation of solar cells and thermoelectric power generation. On the left is shown a perovskite type solar cell that is attracting great attention today. By using a newly developed interface material, we discovered that the cell life can be prolonged significantly. In addition, it was found that even without using LED, power conversion efficiency as high as 11% can be achieved by using tin instead. We are also testing large area devices too. On the right is shown NIMS new thermoelectric materials consisting of most abundant elements on Earth: iron, aluminium, and silicon. While conventional thermoelectric devices use harmful elements, these 3 elements are safe and can be used far more widely. NIMS researchers discovered specific compositions suitable for the power generation device by using material informatics. The developed device can generate 100 microwatt electricity from 1 square centimeters with only 5-degree temperature difference at room temperature.
NIMS considers international collaboration as very important and has several schemes to promote international collaboration. In the following, we will introduce examples based on materials transfer agreement and memorandum of understanding. This is an example of NIMS providing a novel material to many research partners worldwide based on materials transfer agreement. The key material in this case is high-quality hexagonal boron nitride, possessing superb insulating properties as well as an atomic-level flat surface, which make an ideal substrate material for developing 2-dimensional quantum devices. So far, NIMS has provided samples of HBN to more than 250 organizations in 20 countries. NIMS is also involved in collaboration with 9 universities overseas in the fields of energy and environment research as shown in the table. The green color indicates partnerships with G20 members countries such as Australia, China, and Korea. These are examples of ongoing collaborations with G20 national institutes. The topics are quite diverse, ranging from data utilization, co-publication of an international journal STEM, cooperative graduate programs, and neutron scattering. Finally, we would like to draw your attention to Samurai, a database of all the NIMS researchers. You can check their CVs, contact information, research outline, as well as publications and patents. Samurai is fully searchable and open to the public on our website. If you are interested in collaboration with NIMS, please try the Samurai database. Thank you very much for your attention.